上次我们学习向量从我们回顾一下向量从是什么？e to m， so m is a manifold is 是向量从，这是 projection。And each point P, you can have each point P, you can have open input U such that pi inverse of U can be trivialized to R to the R. Okay. And it's a projection. Okay. So that's psychology of phi. By alpha. And then so there's a map in the intersection. You have the map from P to P is the transition map. P to G alpha, later P to P. And usually this would take the general GL. That is a structure group. That's the transition function. Transition function you can have. And then so yeah, so this is so essentially this the向量从的线尾是向量空间，所以基本上的我们可以做普通的线性代数运算，所以you can have the so last time at the end of last time we talked about Whitney sum or direct sum and also direct sum direct product, tensor product, sorry. Tensor product. E1 plus E2, E1 plus E2. That's what we saw last time. And also, dual vector model. We start. And then also exterior product. Exterior product. Like this. So you can take this kind of operation. Okay. 运算，基本运算。That's what we saw last time. And then those are the and then we talk about the so since then you have the in manifold you have a map. The question is if you have a two vector bundle, what's going to happen from here? So this is a bundle map. Such that the bundle map is that each fiber, let's see, EP to E prime, F of P is the F, so this is a linear one. It's always the fiber to fiber. So namely, so if you have a manifold M and then you map point P to f of P, and then at each point you have a vector space, and this map is F is just given by linear. So linear. So this plane is mapped to somewhat like this way. By linear. Okay. So that's a bundle map. You can. So that's a bundle map. And then if you have a bundle map, you can have the following operation. You can pull back the vector bundle. So if you have a map, okay, to the F, you can pull back the vector bundle like this way. That's拉回pull back bundle. Namely, so that F star. So 拉回走。So that's n plus e such that the f of q is equal to pi of b. Okay. So namely, so if you have the you just pull back the fiber, each fiber. So you have n. So let's rename. Let's rename. So this is the So this is M, and M is a map F. You just mapped, and then at each point Q, just copy the image, the fiber at the image of F of Q, fiber. So this is E F of Q, and you just copy them back, copy it back to the original point, the Q, copy it back. That is the F star. E of Q. So that is a Blafoot. So that's a pullback bundle. Okay. Okay, so that's the case. And then you can just include. So the metric, you can only include a metric on the fiber. So EP plus EP to the R or C. Or C. So that's GP. So that's the metric. You can always, so since it's the vector, so each fiber is a vector space, so you can have an inner product at each fiber. So that's the metric. And then so this will satisfy the standard size symmetry and also positive definite. Okay. Positive definite. Okay. So positive definite symmetry means the GP BW is equal to GP WP, and the positive definite and GP and B is 0 and equality holds only when B is equal to 0. What's that? What's it there? 鉴定性。So if you add this kind of metric, so you can have the orthonormal frame. You can have orthonormal frame. So this orthonormal frame. E1, E2, and so on. Orthonormal frame. So the transition function, as I briefly mentioned last time. So transition function is from U alpha frame to U beta frame. Or U beta frame. So this transition function, this orthonormal, is how it maps to this orthonormal place in like this way. And so on. So in this case, structure group. So this transition function. Transition function is this one is called structure group, or physics language, this is called gauge group. Gauge group. Physics language, this is gauge group, but this gauge group can be reduced. Once you introduce such a metric, one can just map from orthonormal frame to orthonormal frame. So therefore, structure group become OR. If it's unoriented, if it's oriented, it becomes SOR. In the case of C, it becomes unitary of R, and then or so this is SUR, special unitary. Okay. 结构群从 GR 越化到 OR。Okay. That's the operation one can do in the vector bond. Okay. And then now we will turn into the principal G bundle. G bundle. Okay. Okay, 举这种。So 举从以后so principal G bundle you just replace the so 向量层的纤维是向量空间，但是矩形层的纤维是离群G。So you have principal G bundle P of N. It's very similar construction. Such that so you have each point. So this is a pi. You have an open neighborhood around the point P. You can have the pre-mesh of U alpha is U alpha cross G. This trivialization is the G. It's a direct product. At each point, you can have okay. So like this way, you can have, and then again, you need to do the following. The transition function. So you have a U alpha plus G to U alpha U theta cross G, and then you have point P and G is mapped H. Let's go H. H is mapped to P G alpha beta P H like this. Okay. So each fiber, when you glue them together, so in other words, so you have the so you have a manifold, and then you have the two region. So one is U alpha, the other is U theta. And then in the overlap, you need to consider the one is the, so at this point you have a U alpha cross G. At this point you have the other trivializer U beta cross G. And in the middle, you need to specify how the fiber is transformed. And this G alpha P is inside a G, group G, Lie group G. Okay. Okay. And then what's nice about the principal G model is we have a free right. Like this way. Okay. So any point I think it's better to use here X instead of F. Okay, so that's X. You can have it. Yeah. Yeah. Maybe I think I should use the right G action is that if you have X. So if you have any point P, so you just have the U dot G such that the pi of UG is equal to pi of U. So this means that if you have the M here, and there's a fiber. We have a fiber here, and then at each fiber, it's better to write the bigger. Like this way. So G. So at each fiber, so the point, pick a point X in the base. So this is called base manifold. And pre-image is this. Pre-image is the Lie group itself, and then the fiber, the 纤维序离群, fiber, and then given the point U, you can always map to U times G by right action. Okay, so always this right action acts each fiber. Okay, therefore, so this right action is the, and then so if you mod P mod G, you get the base fiber. That's a quotient space. Okay. Okay, so that's the case. And then you can also have a 截面, so section. Section is the same thing. So if you have a P of n, pi, and you can have a section. The section such that the s dot pi is equal to identity of n. So that's the section, 截面. 截面 and then 截面 is something like that. So M is mapped to P. Sorry. Maybe I think I should write down that M is here and P is here, and there's a projection, and then so the section is something like this thing, maybe S of M. And 如果这个简体截面有一个简体截面 so M, so if you have such a 简体截面 so principal 简体global section 截面 如果你有简体截面 then this means that the P is equal to, in fact, equal to M plus G. So the trivial bond. So this is trivial bond, which means 平方系统 Okay, trivial bond. So the reason why is that so this is the if and only if. So the reason is that so if you have a trivial bundle, it's easy to get the global section by just adding. Okay, so always you can have global section at the point E. That's the global section. So this is G, and at each point, you just assign each point X. You assign point the 单位元. Okay. So that's the if you how is it? If it is the product, so product bundle, trivial bundle. And on the other hand, if you have a global section, whatever global section you have, okay, you can always bring back such a point by right G action. By right G action, you can always bring back to the origin, the identity element at each fiber. At each fiber, you can have like G action to bring back the identity element. Okay. In that case, you can always have the product structure because so in that case, P is always the can be identified trivial bundle because trivial bundle because the Yeah, so you can always have by right action. You just bring it back to the identity element. Then it's a product bundle. It's just product bundle. So this means that so if you have a global section in principal bundle, it's always triggered. It's kind of boring. It's boring. You have a global section. Okay. And yes. And what's the relation between this 聚从和向量从 ？Okay. So 聚从和向量从 In that case, you can just consider associate bundle. Okay. So associate bundle is if you have the So if you have the representation, G rho. So associate bundle, you just create the principal G bundle to the associate bundle, which we write the P cross G or rho B. So this is principal G bundle. This is the vector bundle. So B is a vector space. And so this is the vector bundle. Vector bundle. And then how do you construct it? So this rho here is it's called representation of G. So this is called representation. Okay. So if you have a G and then G of V, so you just map to any element V. G is mapped to rho G. That acts on the vector space V. So acts on vector space V. And of course, they satisfy the following condition. G2 is essential, or whichever is 1, 2, rho G1, G2, which is rho G1 dot rho G2. That's a representation. Okay. So then you can have the G action on the P cross V in the G action, such that the P dot V dot G is equal to P dot G and the rho G of V. So like this. Okay. Then, so this bundle E, so this is associate bundle, so I call it. Associate bundle is just a quotient space, such that this one is indeed equal to P cross B mod this G action. So since G action is like this way, so namely, so sorry, this is G inverse. So namely, so you have okay. So if you have principal G bundle, like this way. So P to N, like this way. At each point, you have the fiber G. And then pick a point P, you have a right G action, P dot G. Okay. On the other hand, if you have this B, so the vector B is mapped to rho. It's mapped to rho G inverse B. Okay. On the other hand, so on one hand you have a G action on fiber. On the other hand, the G action on the the fiber on the here. Okay. And then so that's also G action. And if you take the the both products, so if you each fiber G cross B, each fiber, okay, of this. So if you have P cross B of N, then given pick a point P, I inverse of P is just a G cross B. Okay? And then take a quotient by G. Quotient by G action, quotient by this G action. Okay, then essentially you kill this G part, and what's left is the vector space. Okay, each fiber becomes vector space. So you just replace this principal G bundle, the fiber G by V. Okay, the vector space. So that's the associated G bundle. And in fact, by using this right G action and representation, in fact, all the how to say, in physics language, matter field, it's called matter field. 武器场，武器场。To the section of the associated bundle. Associated bundle. Matter field in gauge theory. It's called a section associated bundle. For instance, if you learn the quantum field theory and so on, the first thing you learn is something like gauge field and scalar field and so on. But for instance, if you have for instance, sorry, maybe I don't know. It's up to convention. It's convention. Let's take the whatever convention. Let's simple convention. Take. Okay. So in the so this is the character in this some scalar field. Okay. And this phi is called matter field. Matter field. And A is called gauge field. And the phi can be understood the section of this associated bundle. So P cross rho P to M, and you have a section. Or section can be understood phi. This scalar field can be understood as the section of this associated bundle. And then this mu acts on phi by representation of rho. So that's the representation rho. So that's the how the gauge field acts on the scalar field and so on. Okay. Yeah. Okay, so that's the associate bundle one can construct out of the okay. And for instance, yeah. For instance, I mean, you might have heard of it. Let me briefly mention. So from now on, I'm going to introduce From now on, I'm going to law and the Chu-Yu connection or gauge field in the 规范场 and then connection in the curvature of the principal G bundle or vector bundle. So this is a field strength. So this is 长长. So we're going to introduce those concepts to the vector bundle and also principal G bundle. But for instance, so if the gauge group, the G is equal to U1, the theory becomes Maxwell theory. And the G is equal to SU2. You might have known this is the weak force. This is the this called SU2, and the SU3, this is called strong force. And then in particular, this is related to QCD, quantum chromodynamics. And then of course, so if you take the standard representation rho is standard representation doublet. It's called doublet. So the SU2 is something like a alpha beta bar, and alpha bar, and so on. That acts on the B1 and B2 in C. So SU2 can act on C2 like this. This is the standard representation, or it's called in physics like it's called fundamental representation. And that is related to if you use this associate bundle, so this is a representation rho, associate bundle, if you use the sectional associate bundle using this standard representation or fundamental representation, this phi becomes so-called Higgs field. You might have heard. So this phi is called Higgs field. Yeah. Of course, you need to add some kind of like a potential and also the potential and so on. But this sectional associate bundle is related to so-called Higgs field. And for strong forces, of course, you need to introduce fermion. But if you use the fermionic field, C3 times C3 constructed Cripple algebra and so on. Okay, Cripple algebra. So of course, this C3 is corresponding to. So the sections corresponding to. Section is corresponding to so-called Cork field. Okay, Cork field. So this is for QCD. So usually phi corresponding to notation of bosonic field. So people just use Q bar and so on, Q dagger and so on. Anyway, so that's a Fourier field, but which is the, let's say, the standard dimensional C3, but you need to experiment. And then, so this, so the mu is closely related to so-called Z and then Z and W boson. So in the case of SU2, SU3, mu is called corresponding so gluon. So this gauge field is corresponding to gluon. So that's the connection to physics. And then in particular, so you might have heard of it. So say proton or neutron. So you have how to say if you have atoms, you have so classically you have electron is moving around the how to say nuclear, and the nucleus is consists of the proton and neutron. So that's a whatever. Proton plus or neutron neutral. Okay, let's go P and then N and so on. And so on. And you might have heard, so this proton or neutron is made out of the quark. Okay, made out of quark. And then here, but the quark, because of its strong forces, you have to take a singlet, which means the color needs to be white. So you have three kind of quark. You might have heard of it. Red quark. So this is 三元cell. Red and blue and the green is a 三元cell. The green. And if you mix them together, you get the white, right? You get the white. So this three color is represented the basis of this C3. This representation of C3. So anyway, so that is the how associated bundle is related to the construction of physics classically. And of course, in the quantum theory, it's not only this classical construct, classical action, you also need to take into account the quantum correction and so on. But that is not the theme of this lecture. Okay, so okay. Okay, so then let's introduce now 联络。OK， 向量从向的联络 connection。联络 ，I mean， 联络，we already saw the connection in linear geometry. So in the case of linear geometry, you have a tangent bundle. Tangent bundle, and then you have a section. Okay, you have a section here. And what is it called? This section is called what? Do you remember? Vector field, good. So that's a vector field. So this section is called the vector field, and we call it like this way. Okay. And then we had the connection, something like this way. We assign a new vector field. Essentially, what we did, so we just assign like this way, and it satisfies a certain condition, like through linearity and so on. I'm not going to repeat. Essentially, what we did is that and then okay. So the curve, and you have a y-cube field. Y-field. And then what we did is essentially, so you just do the partial transport along this curve. So this x is, this curve is essentially the flow of x. The flow of x. And then the partial transport of y. Okay, if you do the partial transport of y, and then the difference between the vector field y and the partial transport. So this original y to the y tilde is this partial transport. And then this quantity, so the covariant derivative, is just try to measure how they are different. Okay? How they are different. That is del xy. Okay. So the connection is just do the introduce partial transport on the fiber. Okay? On the fiber. And then try to like so the 联络给我们那个不同上的纤维的关系。So different fibers. So the connection will give you the relation between different fiber by just doing partial transport. Okay. And then the difference between them is just the covariant derivative along x. So that's it. So we do the same thing for vector bundle. 向量从向的联络是and if it satisfies the following condition. And Leibniz rule. So those relations is satisfied. Okay, so these three relations, it's very almost same as what we introduced by Riemannian geometry. Okay. In Riemannian geometry, I mean, in Riemann, it's not Riemannian geometry. Riemannian geometry, the connection. I mean, no need to be Riemannian geometry to introduce connection, but to have a Christopher symbol, you need to introduce the metric. Okay. So that's the connection on the usual vector bundle. then there is a section. Okay. There is a section. Okay. And then, so we can do the same thing for if you have a metric. If you have a metric, like this way, on the vector bundle, so the compatible metric so the connection compatible metric is as follows. Okay, that's the case. And in physics, always likes to introduce the basis. So if you have a fiber, so locally, so you have a trivialization. So locally, so you have a trivialization. U alpha by inverse of U alpha is U alpha T alpha plus. Okay. Locally, so you have a trivialization in the vector bundle. So locally, you can introduce some basis in R on the fiber locally. So and then this section Si S1 dot SR is the basis of section. In the you can have the maybe it's better to, so S is equal to sum of S. Okay. So EI, so this is also normal frame. Of this fiber. Okay. And SI is the some basis of section. Then this down XS can be written as XSI plus AIJ EI. Okay. And then this one can be understood as the, so R by R matrix. This can be understood as the GL R. So essentially, this is R by R matrix. R by R 矩阵。So so now for this Aij, so Aij and pairing X is the X is a vector field. This is a vector field, and the Aij is indeed omega 1. omega 1, and then U alpha and GL. So, namely, so the A is a 主键G 的 E 形式。Okay. So the matrix value is one form. Matrix value one form on U alpha. Okay. So this expression is very local expression. It's a very local expression. Okay. And then physics write down this A mu, right? So take X as a local coordinate U alpha. It's just a partial mu. If you take partial mu, this expression is something like this. Partial mu is section Si plus A mu Ij. This A mu Ij is just contract with mu and one form. A mu Ij and then Sj. Okay. This is exactly what appears in the physics. Physics local language. So namely locally, so this AI okay. And the question is how you transform from one to the other. So this is local expression. There is another one. So if you have so if you have the intersection between U alpha and U beta, the question is how you transform one to the other. So if in general it's a structure group is G, so this is Lie algebra G. I mean, vector bundle structure group is G. Okay, structure group or gauge group. G is a structure group. I mean, if you add some metric on the vector bundle, the structure group can become O or SO, or if you consider the complex vector bundle, it becomes SU or U and so on. And then if you introduce some other whatever. Skew symmetric metric, you can introduce SP, like symplectic Lie group too. Given the structure group, this connection will take the Lie algebra value, and then this one is replaced in G, okay? Or Lie algebra G. Sorry, G like this way. If the structure group. And then transition function is just a P and the V. So this is a transition function that is inside an element of G. Okay, in transition function, then what we have is that let me check my notation, how the gauge transfer. So beta sorry, I keep writing the wrong thing. I think my notation is somewhat somewhat floppy. Yeah. Maybe so A alpha is equal to G alpha beta. So one connection to the other connection, you need to do the following transformation. You need to do this following transformation. So this can be derived just how this section is mapped from one to the other. Because in here we take E as a basis of the fiber, and then we know that how basis EI is mapped to the other basis in the other trivialization. And using this transformation, and then use this property, one can derive explicitly this gauge transformation, property, gauge transformation. That's how it mapped. So this is a connection in U alpha. This is the connection U beta. Okay, so that's the connection. Again, essentially the connection is that if you have a vector bundle, E, okay, and then you can just define the paratransport given the point fiber here. The fiber here, and then the nearby fiber here, so it's just schematic. Fiber here, this is the point P, and this is EP, and then so how the paratransport will look like. So this will just so connection will define the paratransport of the section, and then if the section is something like, how to say, something like this section. If you do this section, so this connection will measure how they are deviated from the paratransport. Like this way. Like this. Anyway, it's not global, so I shouldn't write like this. So so at each point you just define how paratransport occurs. So the punchline of connection is 联络是 just 平行移动，定义平行移动的方向。So the connection define paratransport to the vector. That's what the connection do. So connection just define it, like, yeah, how to transfer from one to the other fiber by defining paratransport. What is the curvature? Curvature is also very similar. Let me do a bit about physics, since it's geometry and topology in physics. Okay, so therefore, so this A connection A is one form of you offer a Lie algebra G, value G. Okay? And then people just, physicists often write down like this way. So this A is like this. So this A mu dx mu is a one form. And this ij is a Lie algebra value. So this matrix value is Lie algebra value, right? And this is the basis of Lie algebra. So therefore, A runs for the dimension of G. So, yeah, physicists often write like this. And what is the curvature? Curvature is the assignment of curvature to U. Sorry. Yeah, to U. Two form is assignment of okay. Like this. Okay, of course, they satisfy a very similar property coming from this definition. I mean, it's very similar to how we define the curvature in Riemann geometry. Okay. And then if you use the so they satisfy the several property. So first property is F. The second property is the like this. You can check. Oh, by the way, so this F, G, so here F and G are the function over M. Here is also same. F, G, H. Okay. And then if you use this one, so suppose x is equal to partial mu, and the y is equal to partial nu. Okay, partial nu, and then look at the u alpha. Okay, how the connection acts on u alpha here. Connection is just how it acts is represented like this way. One can just write down as follows. So f, people just write down like this way, and this is people f mu nu. Physicists write down like this way, and then essentially this is partial mu plus a mu. And then plus partial mu and the mu and the nu are exchanged. Okay. But mu are exchanged, and the partial mu and partial nu commute is equal to 0. So you can ignore this one. Then what you have is the following. So that's what you have. And this is exactly the Yang-Mills field strength. In particular, so if you write down the F as a two-form is in fact take U alpha on G, and F is equal to dA plus A wedge A. Okay, so that's the expression of the curvature. Okay. Okay. And in particular, so if you use this transformation, so this is it's called gauge transformation. So this F, so F alpha is related to G alpha beta. Like this one. So this is the gauge transformation. Okay. So now, so this F can be defined, this F can be defined locally twofold. Okay. Locally, so twofold, Lie algebra body twofold. Okay. So 历代数值的一形式 ，okay， 二形式 ，okay， and if you want to define it globally, if you want to globally twofold, what you need to do is that the trace. So since gauge transfer G and G inverse, so if you want to globally define twofold, trace of F is a globally defined two. And if the space-time is this is globally defined. So this one can be globally defined, which means the M, the base manifold M and the Lie algebra value G. No longer Lie algebra value because we already take trace. Okay. Take a trace. And for Yang-Mills theory, S is equal to we take like this Hodge star and the integral over M. Okay. Okay, so let's stop here and take a break for 10 or 15 minutes. And we will move on to the a bit more about the YAML, the power transport, and so on. Okay, let's take a break. algebra?
What it takes.
I think this. Together. Scalar? What is scalar? So it's just numbering. E is the fiber is the rank R vector space, right?
A is 5.
So it's R to the R. And you want to map the section like a. So we have the multiple M, the each for P, and each point you have a fiber to R to the R. EP is essentially.
Oh yeah.
The section at each point section will take some whatever. This is P with some vector. Yeah. So we just act as a this connection of A acts as matrices, acts on this vector. Matrices. R by R matrices.
The matrix acts on which?
AIJ. Yeah, AIJ.
At this point, X. Yeah, this one is X. So it will act on which?
In the section. So this section.
The section is the SJ.
Yeah. SJ. And then it becomes again section, right? So therefore, the base is written as I.
Yeah, I mean, SI is a section. But it is a section.
With some linear combination. Should be good. Section to section, right?
So why do not? If we write like the AIJ X is a matrix, we should act on SJ.
Yes, I or whatever else. That's also okay. That's, yeah. That's another way of writing.
I got it.
Yeah. It's just way of writing.
Okay.
Eventually, so I just want to connect to the right action of the right action of the principal. Yeah.
Oh yeah, I got it.
That's why I wrote like this.
Yeah, I got it. So another thing is, G bundle. The G bundle is just, I mean, rely on the representation. But I mean, we can give different representation on a certain G. So
yeah.
Different representation will give different associated.
Yeah. Okay. But still G bundle. Still G bundle. It's a yeah.
Yeah, I need to be here.
Okay, so let's get started. So two things I need to talk about it. So I just introduced the principal Gibbon law, and I didn't give you some example. So for instance, the last time, so we took a homogeneous space, and in particular, we take this kind of example. Okay. So this is equal to S2 or CP2, CP1, sorry. So SU2 acts on CP1 transiently. Because CP1 can be defined C2, not origin, and C star action. And then SU2 acts on C2. By preserving the length the conventional way. So transiently, and if you fix the point CP1 inside of 1, 0, and then this point is the U1 subgroup acts on the stabilized subgroup. It acts on stabilized subgroup. So U1 acts on the so this one is the E lambda, EI lambda times EI lambda 0 is still 0. Okay, stabilized subgroup. So if you take a quotient, you get the CP1. You get the quotient SU2 U1. This is exactly what we learned. U1 principal G bundle. Principal U1 bundle. So U1 is a fiber of SU2 and then CP1. Okay. And this is we saw many times. So this construction is the U1 Z1 Z2 or Z and W. Oh, sorry. What I'm doing? Yes, sorry. So we know that so this is a hop bundle. S1, S3. Okay. The hop bundle. And then so this SU2 can be understood as ZW minus W bar, Z bar. And if it satisfies the determinant. Okay. For example, the point here, Z and W, is mapped to the point in CP1. CP1. Okay. Okay. And then each fiber it just acts as E to the whatever I lambda Z. I mean is equivalent. But on this fiber, it's actually non-trivial, S3. So if you just pick a point and look at the pre-image, it's a circle bundle, U1. And this is the Hop bundle I introduced many times, like at least twice. And then we already look at the many times or whatever. So if you pick North Pole and South Pole pre-image in S3, become Hop link. That's already introduced. Okay. So this is pi inverse of North Pole, pi inverse of South Pole. You just have a linking up on one. That's Hop bundle. Let's visualize it. Okay. So if you have a Z and W, there's a map. So Z and W in S3, we can map to S2 such that R3 and then actually two times. Yeah. And so that's the is it visible? It's too small. It gets better. The map. So you just write down here Z is equal to A plus B. Z is equal to A plus BI, W is equal to C plus DI, and then you just write down this map. Then they satisfy. So these are the coordinate, and then if you square it, you get this number. This is equal to 1. So therefore, so if you let's call this x, this is equal y, and this is equal z. So x squared plus y squared plus z squared is equal to 1. So this means nothing because we know that a squared b plus b squared plus c plus d squared is equal to 1. So therefore, this map indeed map to S2 inside R3. Okay, inside R3. And then we already know that if we multiply the overall phase factor, E times IT, ZW, by construction, so since it's an absolute value and the whole real part and take Z and W bar, imaginary part Z and W bar, this means that they send to the same point. Okay? So therefore, this E to the IT will give you the whole fiber freedom. And then let's visualize it. First, so I just create the. So here's a slightly. Sorry. Okay. So right side is still I use stereographic projection. S3 is mapped to R3 by like a B, C, D, 1 minus A or something like that. So here, so left-hand side can be understood as S3, and remove 1 point and identify R3. And the right panel is the S2, but S2 you can slice S2. This is S2, but you can slice S1 like this way, right? This slice is given in this ring. And there is a color, right? So this blue color, the pre-image is this blue circle. That is hot fiber. And then the pre-image, so that you can move a little bit to see how. I think around here is the best. Yeah. So if you pick a point in S2, the pre-image this circle, that's a hot fiber inside S3. Okay. And then you can take you can move S1 inside S2 like this way. Yeah. So here you have a north pole, and then here is south pole. Okay. You can see that. So this is south pole pre-image is just go to infinity. Okay. Go to infinity. But in north pole you have a circle. So in R3, so you have pre-image of north pole is this one, high image of north pole. The pre-image of south pole is something like this one. Okay? Pre-image of south pole is like this one. So you can see there, like leading number is 1, right? Leading number 1. So this means that this one is just go infinity and become circle. And so therefore it becomes hot fiber, hot link. So you can easily visualize. Okay, so that's the case. Unfortunately. So this one. Okay. Anyway, so that's the visualization of the hot vibration. Yeah, I can put this one into the e-learning so that you can play around. I mean, it's just a simple code, but you can still visualize the hot vibration like this. That's the case. So that's the one. So another thing, so another way of constructing UN bundle is that as I mentioned, so over S2 is the again, so you have you can just decompose S2 in the at the equator. So you have a northern hemisphere, southern hemisphere, and then just decompose it. Just decompose it. One is here and the other here. Okay. Since it's the disk, so disk is the contractible. Okay. So therefore, you can just have a trivial bundle. So D2 plus S1, then the S1 plus D2. Okay. S1 plus D2. And at the boundary, so at the boundary of D2 is the S2. S2 times, sorry, boundary S2. Boundary D2 is S1. Okay, boundary S1. Yes, this is S1. Boundary of D2. And S1 times S1 is the torus. It's the same thing here. The boundary of D2 is S1. S1 times S1 is torus. If and then you just identify this meridian as a longitude, but the rotation several times, like this way, and eventually you just move to like this way. So this is n time rotation, and glue them back. Then you can construct, in fact, S1 bundle over some, I call it ON, and then S2, like this. You can construct. So indeed, so this is one bundle. So U1 bundle, principal G1 bundle, U1 bundle over S2 is indeed, you get exhausted by this construction. In fact, so it's just the homotopy class of S1 to S1, which is in fact Z, which is Z. Okay, so which Z is corresponding to the element, N is corresponding to Z. Okay, that's how you construct the bundle. Wait a sec. Maybe I told you. Yeah, I told you wrong. Sorry. That's not meridian. So, it's I don't know. It's after how you draw. Maybe I should write down more precisely. I should write down like this one, maybe. No. I'm confused. Yeah, I think this is a way of and it's up to how you draw. So that's another example U1 bundle. Principal U1 bundle. For vector bundle, you can construct the associate bundle based on this principal U1 bundle. And in particular, as I mentioned, so you can have the topological bundle CP1 So last time I introduced so-called the topological bundle of the CP1. So CP we construct like this way. This is a topological bundle. L over C, CP1. Okay. So you just take the CP1. I mean, CP1 is essentially the line inside of C2. So the plane inside of C2. The point in CP1 is the plane inside of C2. And then given a point in the point in L in CP1, so you just take the line or the plane that just on this line, that is topological bundle. So that is called it's topological line bundle, and then this indeed L is in fact if you can start with O, I think O1. We just consider, so here O1 bundle, I consider, so that only just circle one time in meridian and then come back. Okay? O1 bundle, we just consider O1 bundle. O1 with the U1 bundle, and if you consider O1 with this Borel construct, associate bundle with C, okay, and take the CP1, then this is indeed isomorphic to tautological bundle. So this is so now namely, so this tautological bundle is associate bundle, can be obtained by associate bundle over O1. That's another example. Okay, so that's this is associate bundle, a tautological bundle. Associate bundle. So that's another example of vector bundle. Okay. Any question at this moment? Okay. Okay. Okay, so then, as I mentioned, so this connection is given by, is essentially the parallel transport. Let's see the example, how to say, physical realization of this parallel transport. Physical realization. So this 平行移动 So given that so you can do that. Do that some line and the fiber is something like this way. That's schematic. So there's a curve inside M, and then each fiber is just a let's call it a line bundle. Okay. And then section is given by something like suppose section is given by like this way. this S of gamma T. And then, so this nabla gamma dot of T S of gamma of T. If this is 0, so this is called paratransport. So S is called locally, you can just write down this paratransport equation is as follows. So it's really like a geodesic equation. Seriously, it's just analog of geodesic equation. And given the initial condition, one can solve. So one can solve the so this is given. So one can solve it. So given the initial condition as t equals to 0, one can solve this equation locally, okay, given the initial condition. Like this way, one can solve locally. Okay. So that's the paratransport equation. Okay. And the solution is, you can easily see the solution of this equation is something like this way. If it is U1 bundle, suppose G is equal to U1 for the sake of simplicity. So there's only one SI. So there's no, like, this is just there's no matrix U1 bundle, so there's no indices for S. Then one can solve exponential of minus gamma T of A. So you just integrate out connection A. Okay. So you can easily see that this will solve the equation. This equation you can easily solve. So one can solve. So this is S0, and then you can just integrate out the connection A along the curve, and that will give you the paratransport. And this one will appear so-called Aharonov Bohm effect in electromagnetic. What is the Aharonov Bohm effect? So Aharonov Bohm effect is something like this one. So you just put some slit. And there's some wall here, and there's a source here, and then the two particle can take the two path, like this way. Okay. And then put some flux in, let's see, let's write down like this, and B field. So magnetic field like this way. And then you can see the some interference pattern on the wall, like this. Okay. And let's call this a gamma 1 and gamma 2. Okay. And if you solve the Schrödinger equation of in the presence of this gauge field, you will get the phase. The wave function will get the phase such that the so you get the phase such that the gamma 1 AT minus gamma T2 and minus T2. So you get such a phase in particular, so E exponential. Okay. Like this one. Okay, so this is equivalent to saying that the exponential of like this way, dt, and this is equal to exponential of minus and then by Stokes theorem, so this region, let's go R, okay, the area times the area, and this is magnetic flux. So magnetic flux, total magnetic flux that penetrates this region. Okay, you get this phase. So the wave function receives this kind of phase once you have the magnetic field in the middle. And this can be understood as literally the power transport. Power transport. Namely, so if you have, so here space-time, so in space-time you have space-time, you have some path from whatever, gamma 2, like this way. Okay. And each fiber, so there's a fiber. I don't have a space. So let's write it. So at the base you have such a path. But so there's a fiber here. So you start with S0. You start with S0 around here, and then you just do the power transport on the fiber. Okay. And then you end up with ST here. Okay? ST here. So you do the power transfer each fiber. So to each fiber. Do the power transport. So at each point you have a fiber, but due to the magnetic flux inside here, that will give you non-trivial connection. Okay? So if you come back to the original point, the difference between them is e to the minus gamma of t, like this one. The phase will change. That is exactly equivalent to how you integrate magnetic flux that penetrates this region. So that's one, manifestation in physics of the power transfer or gauge connection. Okay. So that's the okay. Okay. Okay, so that's the Fourier transform. Okay. So sorry, I think this is not the right way to draw the picture. I think the right way to draw the picture is as follows. You have a U1 bundle, U1 circle, and you have maybe like this one. And do the transparent transport. You start with S0 here, then you do prior transport, and prior transport, like this. S0 and S3. And the difference between delta E to minus delta gamma T, I think that's the best way to find it. Yeah. Essentially, what we have is that the more generally, so this if you have a principal G bundle, okay, so then base manifold has base manifold has a non-trivial fundamental group. So for instance, this one is pi1 is not 0. You can have a notion of holonomy around this fiber. So we just have like it's hard to draw. I think it's better to draw like this one. So that each point you have at each point you have fiber like this way, okay, and then do the part connection. So to do the power transport, and you just come back original point, you should have a difference between them. So this is a gamma. So that difference is called tau and gamma. And if you have another element of this one, another fundamental group, we have it like this way. Again, that will create you start with this one and then just come back to here, you get like this one. So that will give you another this is gamma 1 and gamma 2, and composition will give you tau gamma 1 plus gamma 2 like this. Okay, like this. Composition. Okay. So therefore, they form the group. In fact, this one will give you pi1 of m to g in homomorphism. I mean, so this difference is given by, so these one are elements in G. So at each fiber Lie group G, and then you have a right G action. So you can identify this, the difference between, once you come back here, is the element in G. Okay? Element G. And you just compose, you can compose them together. That will give you the homomorphism from the fundamental group to the G. This is called holonomy. Holonomy homomorphism or holonomy group. whatever you call it in physics, and then that is closely that will give you notion of the Wilson loop, or like a so-called notion of flat connection. Flat connection is F is equal to 0. Flat connection, notion of flat connection. So, and in particular, if you look at this form, exponential difference, we already saw this expression in linking number. Linking number, when you consider U1 abelian chance elements, U1 abelian chance elements, LDA. So this is M3, and you just consider so-called Wilson loop is E to the 1. So you just consider A1, and then we just consider Wilson loop expectation value. So, sorry, K1, K1, K1. Okay, and then this is given by E to the some number times linking number, K1 and K2. Okay. Okay. And so in the non-abelian case, the order really matters. So here, when you just integrate out, okay, when you integrate out, so this is U1 vector, so U1 bundle, so it's everything commutative. Everything commutative. So it's just number is commutative. But for non-commutative case, so for usual Lie group case, so this gamma needs to be taken the path order way. So P exponential like this. So essentially, what are the integral? A dt1, small dt1. Okay. But this one is actually matrices. Now it takes a Lie algebra value G, small g. Lie algebra value G. So therefore, if you multiply like this A dt, sorry, del t2. Okay, if you multiply like this, or if you multiply del dt2. Del dt1. This is not equal, no longer, because it's matrix valued. Both are. Okay. So therefore, you have to specify how you do the integration. Otherwise, since A is matrix value or Lie algebra value, it's non-commutative. So you need to specify P is a path order way of integrating out to define so-called Wilson loop and so on for non-abelian gauge group. But in any case, this parallel transport appeared and so-called to define the so-called Wilson loop, and also and the so-called flat function. A lot of it. Any questions at this moment? I'm going to skip the definition of the connection. So you can also introduce so-called connection in principal G bundle P to M So that's called Erasmus collection. Erasmus, I don't know. So the precise definition is kind of not so relevant in this lecture, but in the lecture note, the precise definition is given. Yeah. So you can take a look, but I'm not gonna go into the detail. Erasmus is in fact the student of Cartan. Cartan is one of the founder of the construction of this vector bundle, principal G bundle, and so on. So let's look at a bit of Yang-Mills case. So this action here is Yang-Mills. Okay. And the physicist's way of writing, so suppose, so this is the, G Yang-Mills. So this is called coupling constant. And this is metric. And I normalize, so from now on, let's look at the bottom form, it's just a 1. Okay? Square root of determinant G is 1. So that's the case. And then let's look at the equation of motion. Equation of motion is you just take the mu to mu plus slight derivation of mu, and then take del SA, del mu. Okay. So this one, in fact, will give you just is equal to 0 is given by like this. So this is called like this way. Okay. Maybe I think I should specify how it acts on partial mu f mu plus a mu f mu. Okay. So it's now matrix valued, both a mu are Lie algebra valued. So therefore you need to take a commutation. So this is equal to 0 is for Yang-Mills equation. Yang-Mills equation. Okay. For the case of the mathematician's way of writing, so this is using coordinates. So it's a physicist's way of writing. So another way of writing this equation, Yang-Mills equation, is just using one star f dA star is equal to 0. That's another way of writing. In addition to that, they satisfy Bianchi identity. So dA f is equal to 0. Namely, sorry, dA is essentially d plus a, f equal to 0. So this is Bianchi identity. Physicist variable writing is just everything sequence. Is equal to 0. Okay, like this. So that's the two equation, the gauge, so connection or like a gauge field should satisfy classically. Okay, classic. It's a very interestingly, this Yang-Mills equation and so on appear in mathematics, starting from, I would say, late 70s. In particular, the one something called f is equal to star f, or plus minus. It's called self-dual or anti-self-dual. And in self-dual equation, or some people it's called ensemble operation. And what's interesting is that so these are non-linear. So because of this, term, it's become non-linear differential equation, non-linear PDE. So you learn that like a Schrödinger equation, like in quantum mechanics, the Schrödinger equation linear differential equation, which means that the people just mentioned that in the solution, there's this principle superposition. Right? In quantum mechanics, you can just add the solution. Okay, because the Schrödinger equation linear, but for the Yang-Mills equation, you cannot, like if you have one solution, the other solution, if you add them up, it's no longer a solution of the Yang-Mills. That is the meaning of nonlinear. So because of that, solving the Yang-Mills equation is very difficult usually. It's very difficult usually for general manifold M. But somehow these equations knows the original manifold, the differential geometry of this original manifold very well. And in fact, so at the end, Hitchin, Rickenfeldt, Manning, and also Simon Donaldson, and also Attila Bolt. So this is around 78 or 77. This is 82. Around here, so solving this nonlinear differential equation, one can obtain the information about some M and construct some very sophisticated invariants called Donaldson invariants and so on, which I don't think I have a time. I don't have a time to explain. But even though it's just come from the Yang-Mills, okay. So first, people just mathematician constructed the theory of vector bundle and principal bundle. Using the Yang-Mills construct the theory of Yang-Mills or nonlinear gauge theory. And using that one, somehow mathematicians use that equation to construct the invariant model. So it's very like interesting interaction between math and that going on using Yang-Mills. Okay, and in particular, so here, even physically, so F mu u is indeed, we have okay. So there is an additional term because A takes a Lie algebra value. Okay. So therefore, this one gives you the interaction term between group. So interaction term that last time I wrote, right? So like this way. 3-point function, 3-point interaction, and 4-point interaction of group. Okay. So therefore, the quantum mechanically, so this Yang-Mills field is quantum mechanically also very difficult to deal with. Okay. And one of the math because of this interaction. And then another experiment that, so there is a so-called millennium problem. One of the millennium problem math institute created so-called math gap problem. I'm not going to explain what's a math gap problem, but essentially we need to figure a non-perturbable effect of this quantum Yang-Mills theory to somehow, if you just consider non-perturbable effect of quantum Yang-Mills theory, somehow that will create so-called scale of mass. I'm not going to explain what this means, but anyway, quantum mechanically is very difficult to study this Yang-Mills. Okay, let's stop here. Yeah, I need to mention that. So the exam, final exam is the Curvatures, and you can bring iPad but not laptop. Laptop is not allowed, but you can use bring iPad or some like a tablet. This type of computer is okay, but before exam I will check all the internet is switched off for this. Yeah. Do you have a question about the exam? Homework is 50% and the final exam is 50%. And that will determine your final grade. Okay. And then not all students are present here, so just tell your friends if they are not around. The rule of final exam. Okay. And then last lecture is next week is the last lecture, and I will talk about character classes. Let's stop here.
Here. Why there is a vector space for the group for this representation? Why there is vector space?
So we want to construct the vector bundle from the principal G bundle. You need to replace G to B.